Genesis games, like most programming Sega Genesis games, like most video games, involves writing code that controls the game's behavior, including character movement. Here's a basic overview of how developers programmed character movement on the Sega Genesis. 1. Understanding the Sega Genesis. Hardware, CPU. The Sega Genesis is powered by a Motorola 68000 CPU, which is a 16-bit processor running at about 7.6 MHz. It also has a secondary processor, the Zilog Z80, for sound, graphics. The console uses a video display processor, VDP, to handle graphics, with a resolution of 320 by 224 pixels, and a limited palette of 64 colors on screen at a time. 2. Programming language, assembly language. Most Sega Genesis games were programmed in assembly language specifically for the Motorola 68000 CPU. Assembly language is a low-level programming language that is closely related to the machine code that the CPU executes. C language. Some later games or more complex systems might have used C for parts of the code, but the tight control and efficiency required for early console games made assembly the primary choice. 2. Health and safety considerations, assessment of abilities. Before allowing a resident to work, the facility may assess their physical and cognitive abilities to ensure they can safely manage work responsibilities and the commute, medication and health management. For residents who require medication or have health conditions, the facility might coordinate with the resident to ensure they can manage their health while working. 3. Flexibility and support, custom care plans. Assisted living facilities often create individualized care plans, so if a resident is working, their care schedule can be adjusted to accommodate their work hours. Support services. Residents who work might still benefit from services such as meal preparation, housekeeping, or assistance with ADLs when they are not at work. Yes, residents in assisted living facilities can often go out and work if they are physically and cognitively able to do so. Assisted living is designed to support independence while providing help with activities of daily living. ADLs as needed. Here's how it typically works. 1. Independence and freedom, come and go. Most assisted living facilities allow residents to come and go as they please, provided they are capable of doing so safely. This includes going to work, attending social activities, or running errands, transportation. Some facilities may offer transportation services or assistance in arranging transportation to and from work. Yes, if you live in an assisted living facility and are able to drive, you can typically keep your car at the facility and work for DoorDash or a similar service. Here's how it works. 1. Parking and vehicle policies, parking availability. Most assisted living facilities offer parking spaces for residents who still drive. You'll need to check with the specific facility to confirm the availability of parking and any associated fees, vehicle policies. The facility may have specific policies regarding vehicle registration, parking permits, and maintenance. Make sure to comply with these rules to keep your car at the facility. 2. Driving and working, ability to drive. If you are physically and cognitively able to drive safely, you can use your car for personal use, including working for DoorDash or other delivery services, work schedule. Assisted living facilities are generally flexible with resident schedules, so you can work at times that suit you, as long as it doesn't interfere with any required care or services you receive. 3. Health and safety considerations, health assessments. The facility may periodically assess your ability to drive and work, especially if you have any health conditions that could affect your safety. This is to ensure your well-being and the safety of others, medication and health management. If you have specific health needs or medication schedules, you'll need to manage these while working, ensuring that your work does not interfere with your care. 2. Discussing medication during an appointment, reviewing current prescriptions. During your scheduled appointment, whether in person or virtual, you can talk to the doctor about any concerns or questions regarding your current medications, getting new prescriptions. If you need a new prescription or a refill, you can discuss this with the doctor during the appointment. 3. After the appointment, follow-up communication. After your appointment, you might be able to follow up with the doctor's office via phone or their patient portal to discuss any additional concerns about your medication. This, however, would typically be arranged through the doctor's office directly, not via ZocDoc. 4. Social and emotional benefits, sense of purpose. Continuing to work can provide a sense of purpose and fulfillment, which is beneficial for the mental and emotional well-being of residents. Community interaction. Working allows residents to maintain connections with the broader community outside the facility, which can be enriching. 5. Financial considerations, income and benefits. Residents should be aware of how working might affect their income and any benefits they receive, such as Social Security or Medicaid. In summary, residents of assisted living facilities can often continue to work if they are able. The facility will typically support their independence while ensuring their health and safety needs are met. 4. Financial considerations, income impact. If you receive any financial assistance or benefits, it's important to consider how additional income from DoorDash might affect your eligibility for those programs. Insurance. Make sure your car insurance covers you for using your vehicle for work, as some policies may require additional coverage for delivery services. In summary, many assisted living facilities allow residents to keep their cars and work for services like DoorDash, provided they are capable of driving safely and managing their work responsibilities. It's important to check with your specific facility about their policies and ensure that you comply with all necessary rules and regulations. 3. After the appointment, follow-up communication. After your appointment, you might be able to follow up with the doctor's office via phone or their patient portal to discuss any additional concerns about your medication. This, however, would typically be arranged through the doctor's office directly, not via ZocDoc. 4. Prescription refills, requesting refills. If you need a prescription refill, the best approach is to schedule a quick telehealth appointment through ZocDoc. Many doctors can handle prescription refills during these sessions. 5. Contacting the doctor's office, direct contact. If you've already had an appointment and need to contact the doctor's office about your medication, you'll usually need to do so directly, outside of the ZocDoc platform. ZocDoc does not typically provide a messaging system for ongoing communication after the appointment is booked. In summary, ZocDoc is useful for scheduling appointments where you can discuss your medications, but for direct communication about medication outside of these appointments, you would need to contact the doctor's office directly, either by phone or through their own patient portal. Yes, you can use ZocDoc to see both a psychiatrist and a primary care doctor. Here's how you might handle this. 1. Seeing a psychiatrist on ZocDoc, booking an appointment. You can use ZocDoc to find and book an appointment with a psychiatrist. This can be either an in-person visit or a telehealth virtual appointment, discussing mental health concerns. During your appointment with the psychiatrist, you can discuss any mental health concerns, ask for advice, and talk about medication or therapy options. ZocDoc is primarily a platform for scheduling appointments with healthcare providers, including doctors, dentists, and other specialists. It allows you to book in-person or virtual visits, but it is not typically used for directly communicating with a doctor's office about your medication outside of a scheduled appointment. However, here's how you might address your medication needs using ZocDoc. 1. Booking an appointment, in-person visit. You can use ZocDoc to book an appointment with a healthcare provider to discuss your medications in person. This is often the best way to get detailed advice and adjustments to your prescriptions. Telehealth appointment. ZocDoc also allows you to book telehealth virtual appointments, where you can discuss your medications with a doctor online. This can be convenient if you have questions or need a quick consultation. 2. Follow up with a primary care doctor, referral or coordination. If the psychiatrist suggests you follow up with your primary care doctor, you can use ZocDoc to book an appointment with your primary care provider. This could be for further evaluation, blood work, or to discuss any physical health concerns related to your mental health treatment. Continuity of care. Your primary care doctor can help coordinate your overall health care, including any treatments or recommendations from the psychiatrist. Invega Hafira is a long-acting injectable form of the antipsychotic medication paliperidone palmitate. It is used primarily to treat schizophrenia in adults, and is notable for its extended dosing schedule, requiring administration only once every 6 months. Here's an overview of Invega Hafira. 1. Mechanism of action. Paliperidone, Invega Hafira works by affecting the levels of certain chemicals in the brain, particularly dopamine and serotonin. This helps to reduce symptoms of schizophrenia, such as hallucinations, delusions, and disorganized thinking. 2. Dosing schedule. Every 6 months. Invega Hafira is designed for administration once every 6 months, making it the longest-acting injectable antipsychotic available. This extended dosing schedule can improve adherence for patients who struggle with daily or monthly medication regimens. 3. Administration. Healthcare professional. The injection is administered by a healthcare professional, typically in a clinical setting. It is given as an intramuscular injection, usually into the gluteal muscle, the buttocks. Loading dose. Patients are typically stabilized on a shorter-acting form of paliperidone or another antipsychotic before transitioning to Invega Hafira. 4. Benefits. Improved adherence. The long-acting nature of Invega Hafira helps reduce the risk of missed doses, which can be a significant issue in managing chronic conditions like schizophrenia. Stable medication levels. The medication maintains more stable levels in the bloodstream over time, which can lead to better symptom control. 3. Using ZocDoc for both specialties. Scheduling convenience. ZocDoc allows you to manage appointments with multiple healthcare providers easily. You can see your psychiatrist and primary care doctor through the platform, helping to ensure that all aspects of your health are managed effectively. Sharing information. Make sure to inform your primary care doctor about the advice or treatment plan from your psychiatrist so that both providers are aware of your complete health picture. In some cases, ZocDoc might allow you to share appointment details or communicate through patient portals if both doctors use integrated systems. In summary, you can use ZocDoc to see both a psychiatrist and your primary care doctor. This enables you to get specialized mental health advice and follow up with your primary care provider for comprehensive care. 5. Side effects. Common side effects. These can include weight gain, injection site reactions, drowsiness, and increased levels of prolactin, which can affect hormone levels and cause menstrual changes or sexual dysfunction. Serious side effects. There is a risk of more serious side effects, such as tardive dyskinesia, a movement disorder, neuroleptic malignant syndrome, a life-threatening neurological disorder, or significant changes in blood sugar or lipid levels. 6. Considerations. Monitoring. Regular follow-up appointments are necessary to monitor the effectiveness of the treatment and to manage any side effects. Not for everyone. Invega Hafira may not be suitable for all patients with schizophrenia, especially those with a history of hypersensitivity to paliperidone or risperidone. 7. Consultation with healthcare provider. Personalized treatment. As with any antipsychotic treatment, it's important to have a thorough discussion with a healthcare provider to determine if Invega Hafira is the right option. This includes considering the patient's overall health, history with other medications, and specific symptoms. Invega Hafira represents a significant advancement in the treatment of schizophrenia, offering the convenience of biannual dosing while aiming to improve treatment adherence and symptom management. However, as with all medications, it should be used under careful medical supervision. 4. Movement and collision detection. Velocity and acceleration. To create smooth movement, the game might calculate the character's velocity, speed, and acceleration change in speed. This allows for more complex motion, such as gradual speeding up or slowing down. Collision detection. The game checks if the character's new position would cause a collision with other objects, like walls, platforms, or enemies. If a collision is detected, the game might stop the character's movement or trigger an event, like taking damage. 5. Scrolling and background interaction. Scrolling. Many Sega Genesis games feature scrolling backgrounds. When the character moves, the game might scroll the background to give the illusion of a larger world. This involves updating the background position as the character moves. Interaction with environment. The character's movement can also trigger interactions with the environment, such as picking up items, entering new areas, or triggering scripted events. 6. Optimization. Performance. Since the Sega Genesis has limited processing power and memory, developers had to carefully optimize the code to ensure the game ran smoothly. This included efficient memory usage, minimizing the number of calculations per frame, and optimizing the rendering of sprites. To program a sprite or character for a Sega Genesis game, developers use a combination of pixel art, assembly language, or sometimes C, and the console's graphics hardware. Below is an overview of how this process works, including how to create and manipulate sprites. 1. Creating the sprite, character, art, pixel art. Sprites on the Sega Genesis are made using pixel art, where each pixel is individually colored to create a character or object. Due to the limited resolution and color palette, artists must work within constraints, e.g., 320 by 224 resolution and a palette of 64 colors on screen. Tiles. The Sega Genesis uses tiles to create sprites. A tile is a small, 8 by 8 or 16 by 16 pixel block of graphics. Multiple tiles are combined to form a complete sprite. 3. Character movement logic, sprites. Characters in Sega Genesis games are typically represented as sprites, 2D images that can be moved and animated independently of the background. Input handling. The game continuously checks for input from the controller. When a player presses a directional button, e.g., left, right, up, down, the game registers this input. Updating position. Based on the input, the game updates the character's position on the screen. For example, pressing the right button might increase the character's X coordinate, making them move to the right. Animation. Along with updating the position, the game also changes the sprite's image to match the character's action, e.g., walking, jumping. These animations are often done by cycling through different frames of the sprite. 3. Programming the sprite in assembly language, loading sprite data in the game's code. The sprite data, i.e., the pixel information, is loaded into the Sega Genesis's video RAM VRAM. This is typically done using assembly language to control the graphics hardware directly. Setting up the sprite. You define the sprite's position on the screen, size, and which tiles to display. The Sega Genesis has a sprite attribute table set that holds this information. Position, coordinates on the screen where the sprite will appear, X, Y, tile index, which tiles to use from VRAM to form the sprite, attributes. This includes flipping the sprite horizontally or vertically, priority over background layers, and palette selection. 2. Preparing the sprite for the Genesis, graphics tools. Developers use specific tools to create and edit sprites. In the past, these might have been custom tools or specialized software like Deluxe Paint. Today, you can use modern pixel art tools like Sprite or Photoshop, but the artwork must be exported in a format compatible with the Sega Genesis. Converting to sprite data. The pixel art is then converted into a format that the Sega Genesis can understand, typically an array of data representing each tile. This data includes color information, and sometimes a palette index that references the colors to be used. Four. Making the sprite move, input handling. The game continuously checks for input from the controller, e.g., pressing the right arrow key. When input is detected, the code adjusts the sprite's position by changing its X or Y coordinates, updating the screen. The game's main loop updates the sprite's position on the screen based on the player's input or OR logic. The CPU updates the SAT to reflect the new position of the sprite, animation. To animate the sprite, e.g., making the character walk, the game cycles through different tiles that represent different frames of the animation. For example, if the character is walking, the game might alternate between different sprite tiles that show different leg positions. Seven. Tools and development kits, development kits. Sega provided official development kits to game developers, which included tools for coding, debugging, and testing games. These kits often included assemblers, debuggers, and emulators that allowed developers to write and test their code on PCs before running it on the actual Sega Genesis hardware. In summary, making characters move in Sega Genesis games involves programming logic that responds to player input, updates the character's position, handles animations, and interacts with the environment. This process required careful coding, usually in assembly language, to make efficient use of the console's limited hardware capabilities. 5. Handling collisions. Collision detection. The game needs to determine when the sprite collides with other objects, like walls or enemies. This is done by comparing the sprite's position to the positions of other objects. If a collision is detected, the game might prevent further movement in that direction or trigger a response, e.g., taking damage. 6. Optimizing the sprite. Performance, memory management. Since the Sega Genesis has limited memory, developers must manage how many sprites are on the screen at once, and how they are stored. Sprites that are off-screen, are not needed might be unloaded from VRAM to free up space. Sprite limits. The Sega Genesis can handle a maximum of 80 sprites per frame, with a limit of 20 sprites per scanline horizontal line on the screen. If these limits are exceeded, sprites may start to flicker or disappear. Sprite limitations. Example of simple assembly code for moving a sprite. Here's a very simplified idea of what some assembly code might look like to move a sprite in response to input. Load the sprite's x coordinate. Move W, x coord do. Check if the player is pressing the right button. BTST #right button, controller input BQ. No right press. If pressed, increase x coordinate. ADDW number 2 do. No right press. Update the sprite's position. Move W do, x coord. Update sprite attribute table with new x coordinate. Move W do, sprite table ADDR. 7. Tools and emulators. Development tools. Developers use tools provided by Sega and third-party developers to program, test, and debug their games. Today, you can use emulators and modern tools like the Sega Genesis Development Kit, SGDK, to develop games. Testing on hardware. After programming, the game would be tested on actual Sega Genesis hardware to ensure it worked correctly, considering all hardware constraints. Programming games on a calculator, especially graphing calculators, like the TI-84, is a fun and educational way to learn programming concepts. Most graphing calculators allow you to write and run simple programs using a built-in programming language, or by using assembly language. Here's how you can get started. 1. Choosing the calculator model and language. TI-83/84 series. These are some of the most popular graphing calculators used in schools. They support TI Basic, the built-in programming language, and assembly language. Other models. Different calculators have different capabilities. For example, the Casio FX CG50 supports Casio Basic, while HP calculators might support RPN, reverse Polish notation programming. 2. Learning TI Basic for TI calculators. Accessing the program editor. On a TI-83/84, press PRGM. Then scroll to New and press Enter to create a new program. Name your program, and then you'll be taken to the program editor. Writing simple code. TI Basic syntax is straightforward. Here's a simple example of a number guessing game. C1 Rome. Disp guess a number. Disp between 1 and 10. 1A, 10B. Rand int, A, B, C. Input your guess. X. If X equals C, then, disp correct, else, disp wrong, disp the number was C, end. Conclusion. Programming a sprite for the Sega Genesis involves a combination of pixel art creation, data management, and assembly language coding to control the character's movement and interaction with the game environment. Despite the hardware limitations, developers were able to create visually impressive and responsive characters that are still fondly remembered today. Running the program. Exit the editor by pressing second plus quit. To run the program, press PRGM, select your program from the list, and press enter. Then enter again to execute it. 3. Creating simple games. Text-based games. You can create text-based games like Guess the Number, quiz games, or simple choose-your-own-adventure stories. Basic graphics. You can use simple graphics commands to create games like Snake or Pong. Here's a quick example of drawing a line. Comma, running the program. Exit the editor by pressing second plus quit. To run the program, press PRGM, select your program from the list, and press enter. Then enter again to execute it. 3. Creating simple games. Comma, text-based games. You can create text-based games like Guess the Number, quiz games, or simple choose-your-own adventure stories. Comma, basic graphics. You can use simple graphics commands to create games like Snake or Pong. Here's a quick example of drawing a line. Line, 0, 0, 94, 62. This draws a line from the bottom left of the screen to the top right. Comma, control structures. Use loops, for, while, conditionals, if then else, and variables to create more complex games. For example, a simple loop for moving a character on the screen might look like this. Comma, control structures. Use loops, for, while, conditionals, if then else, and variables to create more complex games. For example, a simple loop for moving a character on the screen might look like this. Sir home, 0x0y, repeat Jetkey equals 105, output, y, x, 0, get keek, if k equals 24y plus 1y, if k equals 25y 1y, if k equals 26, x 1x, if k equals 34x plus 1x, C1 Rome, end. This program allows you to move a character O on the screen using the arrow keys. Conclusion. Programming games on a calculator, especially in TI Basic, is a great introduction to programming. You can start with simple text-based games and move on to more complex projects involving graphics and even assembly language if you want to push the calculator's capabilities. It's a fun way to learn programming logic and problem solving, all while working within the constraints of the calculator's limited resources. 5. Transfer and share programs. Calculator to calculator. You can share programs directly between TI calculators using a link cable. Using a computer, you can write programs on your computer and transfer them to your calculator using TI Connect software and a USB cable. This is especially useful for more complex projects or if you're using assembly language. 6. Using online resources. Online forums and communities. There are many online communities like Semadec or TI Planet, where you can find tutorials, code snippets, and support for programming on calculators. Pre-made libraries. You can also find libraries and pre-made games online that you can study or modify. 4. Using assembly language. Why assembly? Assembly language allows you to create much faster and more complex games, but it is harder to learn and use. Learning assembly. If you're interested in writing assembly programs for a TI calculator, you'll need to learn Z80 assembly for the TI 83/84 series. You'll also need a way to transfer your programs to the calculator using a USB cable or through an emulator. Tools. Use an assembler like TASM or Spasm to write and compile your assembly code, and then transfer the compiled program to your calculator. 5. Transfer and share programs. Calculator to calculator. You can share programs directly between TI calculators using a link cable. Using a computer, you can write programs on your computer and transfer them to your calculator using TI Connect software and a USB cable. This is especially useful for more complex projects or if you're using assembly language. Tiger Electronics created the Terminator 2 Judgment Day handheld game in the early 1990s, which was one of their many LCD, liquid crystal display, games. Here's an overview of how they developed the game and the technology behind it. 1. Concept and design. Licensing. Tiger Electronics obtained the rights to create a game based on the popular movie Terminator 2, Judgment Day. The game was designed to capture the essence of the film, focusing on its characters and themes. Game design. The game designers conceptualized gameplay mechanics, level designs, and how players would interact with the game. The aim was to create an engaging experience that reflected the action and narrative of the film. 7. Emulators. Testing on emulators. Before transferring your game to the calculator, you can test it using an emulator, like TI-EMU or WABIT-EMU. This allows you to debug and refine your game without having to repeatedly load it onto your calculator. Conclusion: programming games on a calculator, especially in TI Basic, is a great introduction to programming. You can start with simple text-based games and move on to more complex projects involving graphics and even assembly language if you want to push the calculator's capabilities. It's a fun way to learn programming logic and problem solving, all while working within the constraints of the calculator's limited resources. 2. Hardware development, LCD technology. Tiger Electronics used LCD screens for their handheld games, which were simple, low-power displays. Each game featured a fixed background, with animated characters and objects overlaid on the screen, buttons and controls. The game included buttons that allowed players to interact with the game, e.g., moving characters, shooting, etc. The design needed to ensure that the controls were intuitive and responsive to player input. 3. Game mechanics, gameplay style. The game typically involved simple mechanics, where players would navigate through levels, avoid obstacles, and defeat enemies. The gameplay was often non-linear, with players needing to make quick decisions. Graphics and animation. The graphics were created using a series of static images and simple animations. Designers created sprites for the characters and enemies, and the game used a limited color palette, typical for LCD technology at the time. Microcontroller. 4. Programming, microcontroller. The game was programmed on a microcontroller, which handled the logic and timing of the game. Programming was done in assembly language, or low-level languages that could efficiently manage the limited resources of the hardware. Game logic. The programming included collision detection to determine when the player hits an enemy, scoring systems, and condition checks for winning or losing scenarios. 5. Testing and iteration, playtesting. After development, the game underwent rigorous playtesting to identify any bugs or areas for improvement. Testers would play the game to ensure it was fun, challenging, and worked correctly. Feedback and adjustments. Based on feedback, developers would adjust gameplay mechanics, difficulty levels, and control schemes to enhance the overall player experience. Six. Manufacturing, production. Once the game was finalized, it went into production. This involved creating the physical units, including the LCD screens, circuitry, and housing. Quality control. During manufacturing, quality control ensured that each unit worked as intended and met safety standards. 7. Marketing and distribution, promotional strategy. Tiger Electronics marketed the game alongside the movie's release, leveraging its popularity to attract buyers. The marketing included advertisements, packaging design, and placement in retail stores. Sales and distribution. The game was distributed through various retailers, and its success was influenced by the popularity of the Terminator franchise. Conclusion. Creating the Terminator 2, Judgment Day handheld game by Tiger Electronics involved a multifaceted approach, from conceptualizing the game and designing hardware to programming and manufacturing. The combination of simple yet engaging gameplay, recognizable characters, and effective marketing contributed to its appeal among fans of the film and handheld gaming enthusiasts during that era. While the technology was relatively simple compared to modern gaming, it captured the spirit of the film and provided entertainment to many players. Programming a game similar to Terminator 2, Judgment Day on a calculator can be a fun project, especially if you're using a graphing calculator, like the TI-84. While you won't be able to replicate the full complexity of the original game, you can create a simplified version using TI Basic or a similar programming language for your calculator. Here's a step-by-step guide to get you started. 1. Conceptualize your game, game mechanics. Decide on the core mechanics of your game. For example, you might have the player navigate a character through levels, avoid enemies, and shoot at targets. Objective. Define the objective of your game, such as reaching a certain point or defeating enemies. Graphics. Plan out what your characters and enemies will look like. Remember that on a calculator, graphics will be limited to simple pixel representations. 2. Setting up your environment. 1. Conceptualize your game, game mechanics. decide on the core mechanics of your game. For example, you might have the player navigate a character through levels, avoid enemies, and shoot at targets. Objective, define the objective of your game, such as reaching a certain point or defeating enemies. Graphics, plan out what your characters and enemies will look like. Remember that on a calculator, graphics will be limited to simple pixel representations. 2. Setting up your environment, access the program editor. On a TI-83/84 calculator, press the PRGM button, then select New to create a new program. Give it a name, familiarize yourself with commands. Learn the basic TI basic commands, such as SIR home, disp, input, and control structures if for, while. 3. Basic game structure. Here's a simple example of how you might structure a text-based Terminator-inspired game. This example will focus on a simple shooting game, where the player tries to hit targets. Example game code in TI Basic, C1 Rome, disp Terminator game, disp A, shoot B, quit, 0 score, 0 enemies, repeat get key equals 105, loop until the user presses enter. Randint, 1, 10, enemies, randomly generate enemies. For I, 1, enemies, output, I1, target, show, targets, end, get key, get player input, if k equals 1, if button A is pressed, if enemies, 0, score +1 score I increment, score for hitting a target, disp hit, else, disp miss, end, if k equals 2, if button B is pressed, disp quitting, stop, end, SIR home, disp score, end. 4. Explaining the code, initialization. The game clears the screen and displays the title, game loop. The loop continues until the player presses the enter button, random target generation. It generates a random number of targets enemies, each round, player input. The player can press button A to shoot, or button B to quit, scoring. The score increases if the player shoots at targets, display score. The current score is displayed on the screen. 5. Enhancements and features. Once you have the basic game working, consider adding enhancements, multiple levels, increase the difficulty by adding more enemies, or faster moving targets as the score increases, graphics. Use pixel graphics with the line, circle, or point commands to create a more visual representation of the game. Sound effects. Some calculators support basic sound commands. You can add sound for shooting or scoring. Live system. Implement a system where the player has a limited number of lives or health points. 6. Testing and debugging. Playtest. Run your program multiple times to ensure everything works correctly. Debugging. Check for errors in logic or syntax. TI Basic provides error messages that can help you identify issues. 7. Transferring and sharing. Transfer programs. If you create your game on a computer, you can use TI Connect to transfer it to your calculator. Sharing. Share your code with friends or online communities that focus on calculator programming. Conclusion. Creating a simple game inspired by Terminator 2. Judgment Day on a calculator is an engaging way to learn programming concepts and have fun with your calculator. While the graphics and gameplay will be limited compared to a full-fledged game, you can still capture the essence of the movie and create an entertaining experience. Start simple, and as you become more comfortable with the programming language, you can add complexity and features to your game. Creating a game like Snake's Revenge, a sequel to the classic Snake game, on a calculator involves programming logic for movement, collision detection, and game mechanics. Here's a comprehensive guide on how to design and program a simplified version of Snake's Revenge using TI Basic on a TI-84 calculator, or a similar graphing calculator. 1. Game concept, objective. The player controls a snake that grows longer as it consumes food while avoiding collisions with walls and itself, gameplay mechanics, the snake moves continuously in a direction, the player can change the snake's direction using the calculator's arrow keys, the game ends if the snake collides with the walls or itself, food appears randomly on the screen for the snake to eat, which increases its length. 2. Setting up the environment, comma, access the program editor, press PRGM, then select New, and name your program, comma, familiarize with TI basic commands. Understand commands like CL home, output line, and control structures like if for, and while. 3. Basic game structure. Here's a simplified version of how you might code a Snake game. Due to the limitations of TI Basic, this example will cover the core mechanics without full graphics. Home 0L, 5x 5y, 0d, I length of snake, starting position, direction, 0 equals right, 1 equals up, 2 equals left, 3 equals down, colon, repeat 0, semicolon, main game loop, C1 Rome, for 1L, semicolon, draw the snake, output y, display, snake body, end, output, y, x, 0, semicolon, display, snake head, randint 1, 10f, position, if f equals x, and y equals f, position equals snake head, L plus 1L, semicolon, random food, semicolon, if food, I increase, length, randint, 1, 10, x, I generate, new, food position, end, get keek, semicolon, get player, input, if, k equals 24 and, d number 3, d3, if k equals 25, and d number 0, d0, if, k equals 26, and d1, d1, if k equals 34, and d number 2, d2, semicolon, up, semicolon, down, I left, semicolon, right. If d equals 0, x plus 1x, if d equals 1y 1y, if d equals 2x 1x, if d equals 3y plus 1y, semicolon, move right, move up, move left, move down, if x 0 or x, 10 or y 0 or y 10, collision with walls, disk game over, stop, end, pause 0.5, speed, end, semicolon, control game. 4. Explaining the code, comma, initialization, the game clears the screen and initializes variables for the snake's length, position, and direction, comma, main game loop. This loop continues until the game ends. 4. Explaining the code, comma, initialization, the game clears the screen and initializes variables for the snake's length, position, and direction, comma, main game loop. This loop continues until the game ends, comma, drawing the snake. The snake's body is drawn on the screen by looping through its length and placing asterisks for the body and in 0 for the head, comma, food generation, the program randomly generates a food position. If the snake's head reaches the food position, the length increases, and new food coordinates are generated, comma, direction control. The player can change the snake's direction using the arrow keys, while ensuring it cannot turn directly back on itself, comma, movement. The snake moves in the current direction by updating its x and y coordinates, comma, collision detection. If the snake collides with the walls, the game ends with a message, comma, game speed control. The pause command controls how fast the game updates. 7. Transferring and sharing, comma, transfer programs. Use TI Connect to transfer your game to your calculator, comma, sharing. Share your code with friends or communities focused on calculator programming. Conclusion. Creating a game like Snake's Revenge on a calculator using TI Basic is a rewarding project that helps you learn programming concepts. While the graphics and mechanics will be simplified compared to modern games, you can still create an engaging and fun experience. Start with a basic version, and as you gain confidence, add more complexity and features to enhance your game. 5. Enhancements and features. Once the basic game is functional, consider adding these features, comma, self-collision, implement logic to check if the snake's head collides with its body, comma, scoring system, keep track of the score based on how many food items the snake consumes, comma, multiple levels, increase difficulty by speeding up the game or adding obstacles, comma, graphics, use more elaborate graphics commands to draw the snake and food more visually. 6. Testing and debugging, comma, playtesting, run the game multiple times to test its functionality, comma, debugging, check for errors in logic, and make adjustments based on gameplay experience. While I can't provide the exact source code for Snake's Revenge by Tiger Electronics, I can help you understand how the game might be structured and provide a basic outline that captures the essence of the game mechanics. Here's a conceptual breakdown of how such a game might be programmed in a typical embedded system environment, similar to the original Tiger Electronics devices. Overview of Snake's Revenge game. Logic. 1. Game initialization, set initial values for the snake's position, length, food position, and game state. 2. Main game loop, check for player input to change the direction of the snake, move the snake in the current direction, check for collisions with walls, food, and itself, update the screen display, handle the game over condition. Sample pseudocode for Snake's Revenge. Here's a simple pseudocode representation of how the game might work. Initialize game variables. Length equals 1. Snake position equals ix start. Y start. Direction equals right. Food position equals. Generate random food. Score equals 0. While game is running. Clear screen. Draw food position. Draw snake position. If player input detected. Update direction player input. Move snake position, direction. Move snake position, direction. If snake head collides with food position, length plus equals 1, score plus equals 1, food position equals, generate random food, else if snake head collides with wall or itself, game over, update screen, wait for next frame. Key components explained. 1. Initialization, set the snake's initial length, position, direction, and food location. 2. Input handling, detect player input to change the direction of the snake, e.g., up, down, left, right. 3. Movement logic, update the snake's position based on its current direction, manage the body of the snake by adding a new head and removing the tail if it hasn't eaten food. 4. Collision detection, check if the snake's head collides with the food to grow and increase the score, check for collisions with walls or the snake's body to end the game. 5. Screen drawing, refresh the display by drawing the current state of the snake and food. Conclusion. Creating a game like Snake's Revenge involves programming logic for movement, collision detection, and game mechanics. While the pseudocode outlines the core functionality, translating it into a specific programming language for a calculator or embedded system will require adapting the logic to that environment's capabilities and constraints. If you're interested in implementing this on a specific device, like a TI calculator, let me know, and I can provide more tailored assistance. Example code for a simple snake game in TI Basic: C1 Roam 0L snake 5x5y of the snake 0D 0 equals right 1F for food present length of the starting position direction 1 equals up 2 equals left 3 equals down food variable 1 repeat 0 main game 100p C1 Roam if f equals 1 if food is present randint 1 10 xi generate food's x position randint 1 10 fy generate food's y position 0f set food to not present if x equals fx and y equals fy if snake head meets food l plus 1l of the snake 1f increase length set food to present for 1l output y I draw the snake body end output y x o draw the snake head get key k get player. Input if k equals 24 and d number 3 d3 if k equals 25 and d number 0 d0 if k equals 26 and d number 1 d1 if k equals 34 and d number 2 d2 up I down I left right if d equals 0 x plus 1x if d equals 1y if d equals 2x 1x if d equals 3y plus 1y semicolon, move right I move up, move left, move down. If x1 or x10 or y1 or y10, collision with walls, disp, game over, stop, end, pause 0.1, semicolon, control game, speed, end. Explanation of the code. 1. Initialization, comma, C1 Roam clears the screen, comma, variables L, X, Y, D, and F are initialized, comma, L is the length of the snake, comma, X and Y are the coordinates of the snake's head, comma, D is the direction the snake is moving, comma, F indicates whether food is present, 1 for yes, 0 for no. 2. Main game loop, comma, the loop runs continuously until the game ends, comma, the screen is cleared each iteration with CLR home. 3. Food generation, comma, food is randomly generated if it's not currently on the screen, comma, if the snake's head, X, Y, meets the food, Fx, Fy, the snake length increases, and food is set to be present. 4. Drawing the snake, comma, a loop draws the snake body using asterisks, with the head represented as in 0. 5. Player input, comma, the player can change the snake's direction using arrow keys. The snake cannot turn directly back onto itself. 6. Movement logic, comma, the snake moves based on the current direction, comma, the position is updated accordingly. 7. Collision detection, comma, if the snake collides with the walls, out of bounds, the game ends, and a message is displayed. 8. Game speed control, comma, the pause command controls how fast the game updates. Additional features to consider, comma, self-collision, implement logic to check if the snake's head collides with its body, comma, scoring system, keep track of how many food items the snake consumes, and display the score, comma, obstacles, add random obstacles that the snake must avoid to increase the challenge, comma, advanced graphics, use line, circle, or other graphical commands for better visuals. Conclusion. This basic version of Snake on a TI-84 calculator demonstrates the core gameplay mechanics. You can expand upon this foundation by adding more features and complexity to make the game more engaging. Enjoy programming your own version of Snake. Creating a game like Snake's Revenge with enemies on a calculator can be a fun challenge. Below, I'll outline a simple implementation of enemies within the context of the Snake game using TI Basic. The enemies will move randomly on the screen, and if the snake collides with an enemy, the game will end. Example code for Snake game with enemies in TI Basic. Here's a basic example that includes enemies for your Snake game. C1 Roam, 0L, semicolon, length of the snake, 5x5y, semicolon, starting position of the snake, 0D, 1F, semicolon, direction, 0 equals right, 1 equals up, 2 equals left, 3 equals down. Food variable 1. For food present, 2e, semicolon, number of enemies, colon, randint, 1, 10, x, random enemy x position, colon, randint, 1, 10, e, random enemy y position, colon, repeat 0, semicolon, main game loop, C1 Roam, if f equals 1, semicolon, if food is present, randint, 1, 10, fx, generate, food's x position, randint, 1, 10, fy, generate, food's y position, 0f, semicolon, set food to not present, if x equals fx, and y equals fy, if snake head meets food, L plus 1L, of the snake, 1f, semicolon, increase length, I set food to end, semicolon, move enemies randomly randint, 1, 4, m, direction for enemy, if m equals 1x plus 1x, if m equals 2, ey1 if m equals 3, x1x, if m equals 4ey plus 1ey, semicolon, random move, semicolon, move enemy right, move enemy up, move enemy left, move enemy down, semicolon, check enemy collision, if x equals x, and y equals e, disc game over, stop, end, semicolon, draw enemy, output, ax, x, draw enemy, pause 0.1, semicolon, control game, speed, end. Present, for I, 1, L, snake body, end. Output, Y, X, 0, snake head. Output, Y, I, draw the, semicolon, draw the, get keek. Input, if k equals 24, and d number 3, d3, if k equals 25, and d number 0, d0, if k equals 26, and d number 1, d1, if k equals 34, and d number 2, d2, semicolon, get player, semicolon, up, semicolon, down, I left, semicolon, right, if d equals 0, x plus 1x, if d equals 1y 1y, if d equals 2x 1x, if d equals 3y plus 1y, semicolon, move right I move up, move left, move down, if x1 or x10 or y1 or y10, collision with walls, disk game over, stop, end. Explanation of the code. 1. Initialization, comma, similar to the previous example, we set the initial variables for the snake, food, and a random enemy's position. 2. Main game loop, comma, the loop runs until the game ends, comma, the screen is cleared each iteration with C1 roam. 3. Food generation, comma, random food coordinates are generated, and the snake's length increases when it consumes food. 4. Drawing the snake, comma, the snake is drawn using asterisks, with the head represented as in 0. 5. Player input, comma, the player can control the snake's direction using the arrow keys. 6. Movement logic, comma, the snake moves based on its current direction. 7. Collision detection, comma, if the snake collides with the walls or itself, the game ends, comma, if the snake collides with an enemy, represented by an X, the game also ends. 8. Enemy movement, comma, the enemy moves randomly in one of 4 directions each turn, up, down, left, right, comma, the enemy's position is updated based on a random integer. 9. Drawing the enemy, comma, the enemy is drawn on the screen at its current position. 10. Game speed control, comma, the pause command controls the game's update speed. Additional features to consider, comma, multiple enemies, expand the code to have multiple enemies by creating arrays for their positions and looping through them, comma, different enemy behaviors, implement more complex enemy movement patterns, e.g., chasing the snake, comma, scoring system, keep track of how many food items the snake consumes, and display the score, comma, game levels, increase difficulty as the player scores more points by speeding up the enemies, or adding more. Creating a more complex version of a game like Snake's Revenge with ammunition, food, and guns involves adding additional mechanics for shooting and resource management. Below, I'll provide an outline and some example TI basic code to help you implement these features into your game. Game mechanics overview. 1. Ammo management. The player can collect ammo that allows them to shoot. 2. Food. The snake can eat food to grow in length. 3. Guns. When the player collects a gun, they can shoot at enemies. 4. Enemies that the player can shoot at will move randomly. Conclusion. This example provides a basic framework for implementing enemies in a snake game on a calculator. You can expand upon this foundation to create a more complex and engaging game experience. Have fun programming. Example code for snake game with ammo, food, and guns in TI Basic. Here's an extended version of the previous snake game that incorporates these elements. Sir home, 0L, semicolon, length of the snake, 5x5y, semicolon, starting position of the snake, 0D, 1F, semicolon, direction, 0 equals right, 1 equals up, 2 equals left, 3 equals down, semicolon, food variable 1, for food present, 0A, ammo count, 1G, semicolon, gun variable 1 if player has a gun, 0 if not, randint, 1, 10, xi random enemy x position, randint, 1, 10, ei random enemy y, position, randint, 1, 10, fx, random food x position, randint, 1, 10, fyi random food y, position. Repeat 0. C1 roam. If f equals 1, if semicolon, main game 100p, semicolon, if food is present, x equals fx, and y equals fy, L plus 1L, increase length, of the snake, randint, 1, 10, fx, generate, new food, randint 1, 10 fy, 1f, I set food to, present, end, for 1, 1L, snake body, end, output, y, x, 0, snake head, output, y, I, draw the, semicolon, draw the, if, g equals 1, semicolon, if player has a output, 1, 1, ammo, display ammo count, a, get keek, semicolon, get player, input, if, k equals 24, and d number 3, semicolon, up, d3, if, k equals 25, and d number 0, semicolon, down, d0, if k equals 26, and d number 1, semicolon, left, d1, if, k equals 34, and d number 2, semicolon, right, d2, if k equals 105, and a, 0, semicolon, if enter is pressed and ammo is available, A1A, use 1 ammo, I logic to check if shot hits, enemy, if x equals x, and y equals e, semicolon, enemy is hit randint, 1, 10, x, semicolon, respawn, enemy, randint, 1, 10, ey, if d equals 0, x plus 1x, if d equals 1y 1y, if d equals 2x 1x, if d equals 3y plus 1y, semicolon, move right, move up, move left, move down, if x1 or x10 or y1 or y10, collision with walls, disp, game over, stop, end. If x1 or x10 or y1 or y10, collision with walls, disp game over, stop, end, semicolon, move enemies randomly randint, 1, 4, m I random move, direction for enemy, if m equals 1, x plus 1x, semicolon, move enemy right, if m equals 2, ey1 ey, move enemy up, if m equals 3, x1x, semicolon, move enemy left, if m equals 4, ey plus 1 ey, semicolon, move enemy down, semicolon, check for enemy collision, if x equals x, and y equals e, disp game over, stop, end, semicolon, check for gun pickup, random chance, find a gun, if randint, 1, 10, equals 1, I 10% chance to, 1g, semicolon, player picks, up a gun, output 2, 1, gun acquired, pause 0.1, I control game, speed, end. Explanation of the code. 1. Initialization, comma, the game initializes the snake's length, position, direction, and whether food and guns are present. 2. Main game loop, comma, the loop continues until the game ends, comma, the screen is cleared each iteration. 3. Food generation, comma, food is randomly generated, when the snake's head meets the food, the snake grows, and new food is spawned. 4. Ammo and guns, comma, the variable A tracks the player's ammo count, and G indicates whether the player has a gun, comma, if the player has a gun and presses the enter key, 1 unit of ammo is used, comma, there's a chance, 10%, that the player finds a gun while playing. 5. Drawing the snake and ammo, comma, the snake is drawn, and if the player has a gun, the ammo count is displayed. Additional features to consider, comma, multiple enemies, add more enemies by creating arrays for their positions and managing their movements, comma, scoring system, track how many enemies the player shoots, and how much food they consume, comma, game levels increase the game's difficulty as the player scores points, by speeding up the enemies, or adding more obstacles. Conclusion. This example shows how to integrate ammunition, food, and guns into a snake game on a calculator. You can expand and modify this code to create a more engaging and complex gameplay experience. Enjoy programming. 6. Player input, comma, the player can change the snake's direction using the arrow keys. If the player has ammo, they can shoot. 7. Movement logic, comma, the snake moves in the current direction, 8. Collision detection. Comma, if the snake collides with the walls, the game ends. Comma, if the snake collides with an enemy, the game ends. Comma, if the player shoots an enemy, i.e. the snake's head is in the same position, the enemy respawns. 9. Enemy movement. Comma, the enemy moves randomly in one of 4 directions each turn. 10. Game speed control. Comma, the pause command controls how fast the game updates. To implement a level progression system in a game like Snake's Revenge on a calculator using TI Basic, you'll need to create a mechanism that allows the player to advance to the next level after meeting certain conditions, such as reaching a score or consuming a specific amount of food. Overview of level progression. 1. Level initialization. Each level can have different conditions for winning or completing the level. 2. Score tracking. Track the player's score to determine when they can advance to the next level. 3. Level increase. Increase the difficulty or change parameters when the player reaches the next level. Example code for level progression in TI Basic. Here's an extended version of the previous Snake game example that includes level progression. End. 4. 1. 1. L. Snake body. End. Output. Y. X. 0. Snake head. Output. Y. I. Draw the. Semicolon. Draw the. If. G equals 1. Semicolon. If player has a gun. Output. 1. 1. Ammo. A. Display ammo count. Output. 0. 1. Score. S. Display score. Output. 0. 10. Level. LVL. Display level. Get geek. Semicolon. Get player. Input. If. K equals 24 and D number 3. Semicolon. Up. D3. If K equals 25 and D number 0. Semicolon. Down. D0. If K equals 26 and D number 1. Semicolon. Left. D1. If K equals 34 and D number 2. Semicolon. Right. D2. If K equals 105 and A. 0. If enter is pressed and ammo is available. A1A. Use 1 ammo. Semicolon. Logic to check if shot hits. Enemy. If X equals X and Y equals E. Semicolon. Enemy is hit randint. 1. 10. X. Respawn. Colon. C1 roam. 0L. Semicolon. Length of the snake. 5x5y. Semicolon. Starting position of the snake. 0D. 0 equals right. 1F. Semicolon. Direction. 1 equals up. 2 equals left. 3 equals down. Food variable 1. For food present. 0A. Semicolon. Ammo count. 0G. Gun variable 1 if player has a gun. 0 if not. 0S. I score. 1 LVL. Current level. Colon. Randint. 1. 10. XI random enemy X. Position. Colon. Randint. 1. 10. EY. Random enemy Y position. Colon. Randint. 1. 10. X. Random food X position. Colon. Randint. 1. 10. FY. Random food Y position. Colon. Repeat O. Sirhome. If F equals 1. If. Semicolon. Main game loop. Semicolon. If food is present. X equals FX. And Y equals FY. L plus 1L. Increase length. Of the snake. S plus 10 SI increase score. By 10. Randint. 1. 10. FX. Generate. New. Food. Randint. 1. 10. FY. 1F. Semicolon. Set food to. Present. End. Enemy. Randint. 1. 10. EY. If X1 or X10 or Y1 or Y10. Collision with walls. Disk game over. Stop. If D equals 0. X plus 1X. Semicolon. Move right. If D equals 1Y1Y. Semicolon. Move up. If D equals 2X1X. Semicolon. Move left. If I. D equals 3. Y plus 1Y. Semicolon. Move down. End. Semicolon. Move enemies randomly randint. 1. 4. M. Semicolon. Random move. Direction for enemy. If M equals 1X plus 1X. If M equals 2EY 1EY. If M equals 3X1X. If M equals 4. EY plus 1EY. Semicolon. Move enemy right. Move enemy up. move enemy left, move enemy down, semicolon, check for enemy collision, if x equals x, and y equals e, disp, comma, game over, stop, end, semicolon, check for gun pickup, random chance, find a gun, 1g, if randint, 1, 10, equals 1, 10% chance 2, semicolon, player picks up a gun, output 2, 1, gun acquired, semicolon, check for level up, every 50 points, if S 50 LV LJ, LVL plus 1 LVL, I increase. Level, disp level up message, pause 1, moment, sear home, for next level, semicolon, display, semicolon, pause for a, I clear screen, pause 0.1, I control game, speed, end. Explanation of the code. 1. Initialization, comma, the game initializes variables for the snake's length, position, direction, food, ammo, guns, score, and level. 2. Main game loop, comma, the loop continues until the game ends, comma, the screen is cleared each iteration. 3. Food generation, comma, food is randomly generated. When the snake's head meets the food, the snake grows, and the score increases. 4. Ammo and guns, comma, the variable A tracks the player's ammo count, and G indicates whether the player has a gun, comma, when the player uses a gun, the ammo count decreases. 5. Drawing the snake, score, and level, comma, the snake, score, and level are drawn on the screen. 6. Player input, comma, the player can control the snake's direction using the arrow keys. If the player has ammo, they can shoot. 7. Movement logic, comma, the snake moves in the current direction. Additional features to consider, comma, different enemy behaviors. You can introduce stronger enemies or different enemy movement patterns in higher levels, comma, more levels. You can add more levels by changing parameters, such as increasing enemy speed or adding obstacles, comma, level-specific challenges. Introduce unique challenges for each level, like time limits or specific enemy types. Conclusion. This code demonstrates how to implement a level progression system in a snake game on a calculator. You can expand and modify this code to create a richer gaming experience with multiple levels and increasing difficulty. Enjoy programming. 8. Collision detection, comma, if the snake collides with the walls or itself, the game ends, comma, if the snake collides with an enemy, the game ends. 9. Enemy movement, comma, the enemy moves randomly in one of 4 directions each turn. 10. Level up mechanic, comma, if the score reaches a multiple of 50 e.g., 50, 100, 150, the level increases, and a message is displayed, comma, you can adjust the score needed for leveling up by changing 50 LVL. 11. Game speed control, comma, the pause command controls the game's update speed. Creating a basic version of a game inspired by Metal Gear on a calculator using TI Basic can be quite complex due to the limitations of the platform, but you can implement fundamental mechanics like stealth, movement, and simple enemy interactions. Below is a simplified example of how you might set up a basic Metal Gear-like game. Overview of the game, comma, the player can move around the screen, trying to avoid enemies, comma, if the player touches an enemy, the game ends, comma, the player can collect items like keys to complete levels. Example code for a simple Metal Gear-inspired game in TI Basic. Sear home, 1p, 1 to 10 for x, 1q, 1 to 10 for y, 3e1 x 3e1y, 6e2 x 6e2y, 0k, 1 LVL, 0s, semicolon, player position, semicolon, player position, enemy 1 position, enemy 2 position, semicolon, key collected, current level I score, colon, repeat 0, semicolon, main game 100p, C1 ROM, output, 0, 1, score, S, display score, output, 0, 10 level, LVL, display level, output, Q, P, P, draw player, output, E1Y, E1X, E1, draw enemy 1, output, E2Y, E2X, E2, draw enemy 2, semicolon, check for key pickup, if P equals 5, and Q equals 5, Player reaches key location. 1K. Player collects the key. S plus 10S. Increase score. Disp key acquired. Pause 1. Pause for a moment. Key. Player input get key. If 1 equals 24, and Q, 1 Q 1 Q. If 1 equals 25, and Q 10 Q plus 1 Q. Semicolon. Up. Down. If I equals 26 and P 1 P 1 P. Left. If 1 equals 34 and P 10, P plus 1 P. Right. Semicolon. Enemy movement randint, 1 4, M. Random move direction for enemy 1. ITM equals 1E1X plus 1E1X. Move enemy 1 right. If M equals 2E1Y 1E1Y. Move enemy 1 up. If M equals 3, E1X 1E1X. Move enemy 1 left. If M equals 4E1Y plus 1E1Y. Move enemy 1 down. Randint, 1 4, N. Random move direction. If N equals 1E2X plus 1E2X. Move enemy 2 right. If N equals 2E, 2Y 1E2Y. Move enemy 2 up. If N equals 3E2X 1E2X. Move enemy 2 left. If N equals 4E2Y plus 1E2Y. Move enemy 2 down. For enemy 2. Semicolon. Check for collisions with enemies. If P equals E1X, and Q equals E1Y, or P equals E2X and Q equals E2Y, disp, comma, game over. Semicolon. Check for win condition, for example, collecting a key. If K equals 1, disp level complete. Pause 2. Pause for a moment. LVL plus 1 LVL. Increase level. 0K. Reset key collection. 0S. Reset score for next level. Pause 0.1. Control game speed. End. Explanation of the code. 1. Initialization, comma. The game initializes player position, P, Q, enemy positions, E1X, E1Y for enemy 1, and E2X, E2Y for enemy 2, key collection status, K, current level, LVL, and score, S. 2. Main game loop, comma. The loop runs until the game ends, comma. The screen is cleared each iteration. 3. Drawing the player and enemies, comma. The player, P, is represented by a P, and enemies, E1 and E2 are represented by E1 and E2. Their positions are displayed on the screen. 4. Key pickup, comma. If the player reaches the position 5, they collect a key, which increases their score. 5. Player input, comma. The player can move using arrow keys. The movement is restricted within the bounds of the screen, 1 to 10. 6. Enemy movement, comma. Each enemy moves randomly in one of 4 directions. 7. Collision detection, comma. If the player collides with an enemy, the game ends displaying game. 7. Collision detection, comma. If the player collides with an enemy, the game ends, displaying game over. 8. Level completion, comma. If the player has collected the key, they receive a level complete message, the level increases, and the score resets for the next level. 9. Game speed control, comma. The pause command controls the game's update speed. Additional features to consider, comma. More levels, add more levels with different enemy types, movement patterns, or challenges, comma. Different weapons, introduce weapons, or items that the player can collect and use against enemies, comma. Stealth mechanics, implement stealth mechanics, where the player can hide from enemies or distract them. Conclusion. This code provides a foundation for a Metal Gear-inspired game on a calculator. You can expand upon this basic setup by adding more complex mechanics, features, and challenges to create a more engaging experience. Enjoy programming. Creating a full NES game like Snakes Revenge involves complex programming and assembly language specifically designed for the NES, Nintendo Entertainment System architecture. NES games use the 6502 processor, and writing code for it requires knowledge of low-level programming, graphics handling, and sound management. While I can't provide a complete source code for Snakes Revenge, I can give you an outline of how to structure such a game, and some example snippets in NES assembly language to help you get started. Game structure overview. 1. Initialization, set up the NES environment, including the PPU, picture processing unit, for graphics, load graphics and define sprite data. 2. Game loop, handle input from the controller, update game logic, e.g., moving the snake, checking for collisions, render graphics on the screen, implement sound effects. 3. Game states, handle different states like the title screen, gameplay, game over, etc. Example assembly code snippets. Below is an example of how you might structure some parts of an NES game, like Snake's Revenge. This is a simplified example, and does not represent a complete game. Semicolon. Example input reading read input. LDA $4,016. Controller 1. And number 0 $1. Button A is pressed. BQNOA. JSR snake move right if A is pressed NOA. RTS. I read. Semicolon. Check if. Semicolon. Move snake. Semicolon. Example game update game. Semicolon. Update snake position. Check for collisions. RTS. Semicolon. Example rendering render. Semicolon. Render snake and background. RTS. Semicolon. Example load sprite routine load sprites. Semicolon. Load sprite graphics into PPURDS. Semicolon. Example load background routine load background. Semicolon. Load background graphics into PPURDS. Semicolon. Example initialization code. Reset. Say. Interrupts. CLD. Decimal mode. LDX number $40. Pointer. TXS. INX. Register. SDX $2,000. Control registers. SDX $2,001. And background rendering. JSR load sprites. Semicolon. Disable. Semicolon. Clear. I set stack. Semicolon. Initialize X. I set PPU. Enable NMI. I load sprite. Data. JSR load background. Load background data. Key components to develop. 1. Graphics, create and load sprite graphics for the snake, food, and enemies, use the NES's PPU to manage sprites and background tiles. 2. Input handling, read inputs from the NES controller and translate them into actions, moving the snake, etc. 3. Game logic, implement the mechanics of the game, growing the snake, eating food, detecting collisions with walls or enemies. 4. Sound, use the NES APU, audio processing unit, to create sound effects for actions like eating or losing a life. 5. Levels and progression, define how levels progress, and any changes in difficulty. Resources to learn NES. Development, Nerdy Nights, a great resource for learning NES programming from the ground up, NES Tutorials, a detailed guide to NES development that covers various topics, including graphics, sound, and gameplay mechanics, Fami Tracker, a tool for creating music for NES games, NES Dev, a community and wiki that provides a wealth of information about NES programming. Conclusion. Developing a game like Snake's Revenge for the NES requires a deep understanding of the system's architecture and programming principles. The example snippets provided here are a starting point, but building a complete game will involve significant effort and learning. Use the resources mentioned to dive deeper into NES development and expand upon the provided structure. Happy coding! Game structure overview. 1. Initialization, set up the Sega Genesis environment, including memory mapping and hardware initialization, load graphics, sound, and any necessary data. 2. Game loop, handle input from the controller, update game logic, e.g., player movement, enemy physics, render graphics on the screen, implement sound effects. 3. Game states, manage different states like the title screen, gameplay, game over, etc. Example assembly code snippets. Here's a simplified example of some of the components that might go into a Sonic-like game. Creating a game like the original Sonic the Hedgehog is a complex task that involves programming, game design, and understanding the specific hardware architecture of the Sega Genesis. The original Sonic game was developed using assembly language for the Motorola 68000 processor, and also involved a custom graphics engine for rendering sprites and backgrounds. While I can't provide the complete source code for Sonic the Hedgehog, I can outline the key components and provide some example code snippets to help you get started on your own Sonic-like game. Example initialization code, initialization code, start, initialize the Sega Genesis system, JSR init system, function to initialize system, JSR load graphics, I load sprite, graphics and backgrounds, JSR load music, load, background music, main loop, JSR read input, read, controller input, JSR update game, state player movement, physics, JSR render, I update game, I render, graphics to the screen, JMP main loop, repeat the main loop, example input handling, read input, move W, $10,004, do, read, controller input from port, N, W number $0001, D0, check if, button A is pressed, BQ, Nobutona, JSR, move right, move, Sonic right if A is pressed Nobutona, RTS. Example player movement, I move Sonic move right, ADD, W number $01, Sonic's, increment Sonic's X position, check for collision, etc., RTS. Example rendering, render function render, I clear the screen, JSR clear screen, draw the player, JSR draw sprite, RTS. Key components to develop. 1. Graphics, create sprite graphics for Sonic and other game elements, enemies, rings, etc., use tile maps for backgrounds, which can be loaded into VRAM. 2. Physics and movement, implement momentum and gravity to make Sonic feel fast and responsive, add features like jumping and rolling. 3. Level design, create multiple levels with various layouts and challenges, use a level editor to design and arrange tiles, enemies, and collectibles. 4. Sound, use the Sega Genesis's audio hardware to create sound effects and music. 5. Collision detection, implement collision detection to handle interactions between Sonic enemies and the environment. 6. Game states, manage game states like starting screens, gameplay, and game over screens. Resources to learn Sega Genesis. Development, Sega Genesis Development Wiki, a comprehensive resource for information on programming for the Sega Genesis, including hardware details and programming tips, SGDK, Sega Genesis Development Kit, a C-based development kit that simplifies the process of creating games for the Genesis, Retro Game Dev, offers tutorials and resources for creating retro games, including for the Sega Genesis, assembly language books, familiarize yourself with assembly programming, specifically for the 68000 architecture. Conclusion. Developing a game similar to Sonic the Hedgehog for the Sega Genesis requires a strong understanding of assembly language, hardware, and game design principles. The example snippets provided here give you a starting point, but building a complete game will involve significant effort and learning. Utilize the resources mentioned to dive deeper into Sega Genesis development and expand upon the provided structure. Happy coding!